Okay, I'm going to get going because I've got quite a lot to say and there's just a little bit of time. So maybe there'll still be a few people to show up, but I'm going to get going. So what I want to talk about is Seccomp. You can hear me fine down the back? Yep, good. Seccomp, it's a facility for limiting the set of system calls an application's allowed to make. And the point is the kernel provides around about 400 different system calls. There is a manual page called syscalls where you can see that list of system calls. The way most programmers think about system calls is it's a way of asking the kernel to get something done. The way attackers think about system calls is this is one more way I might try and compromise the system. And the thing is, though there's about 400 different system calls, most programs only use a small set of those system calls. It'd be really typical that the average program would use less than 40 system calls in its life, 40 different system calls in its lifetime. So less than 10% of the available system calls. Those other system calls, if the program makes those system calls, then somehow this is unexpected, illegitimate. Perhaps it's happening because the program's been compromised and tricked into executing unexpected code, which so then we know that something's wrong. And if the program's trying to make those sort of unexpected system calls, we want to stop it from doing that. And that's what Seccomp's about. It's a mechanism for stopping programs making illegitimate, unexpected system calls. And the idea then is, because you've limited the set of system calls that an application is allowed to make, you've effectively reduced the attack surface on your kernel. Now a compromised application can't be used to try out all of those other system calls to see, can we do something that makes the system do something unexpected, somehow achieve a compromise. Okay, Seccomp's actually been around for a long time. It was the first version of Seccomp was back in 2005, and the way you enabled it was to write one into a certain proc PID file. But what we had back there at the beginning was a very limited form of Seccomp filtering. Basically, you wrote one into that file, and after that, the program could make a total of 4 different system calls, and only those 4. Read and write, so you could read and write files, exit, so the process could terminate, and sig return. Now, sig return is a special system call that's used in the implementation of signal handlers. So in summary, you could do file I/O, but you couldn't actually open files. You could only do file I/O on files that had already been opened before we went into Seccomp mode. You could terminate, and you could catch signals. Made any other system call, then the program was killed with a sig-kill signal. Now, the original intention here was actually something quite different. The kernel developer who added this feature to the kernel had the idea of creating a marketplace in CPU cycles. In other words, you've got some spare cycles on your machine. You could say to people on the internet, hey, I'll run code of yours on my machine. You can give me a little bit of money, some sort of micropayment maybe, and I'm going to run that code inside a sandbox that employs Seccomp. And you could run that code on your machine and feel fairly safe that it couldn't do any damage on your machine, because the code couldn't open new files. It couldn't do just about anything except read and write existing files and terminate and catch signals. That was the original idea. This didn't really take off, this idea of selling your CPU cycles, but that was the original idea. Now things started to get interesting only a few years later in Linux 3.5, 2012, when there was a new Seccomp mode added called filter mode. Now this was such a radical change that oftentimes this version of Seccomp was called Seccomp 2 because it was such a radical expansion in the functionality. And the way you enable this, this Seccomp filtering is with a certain system call, PRCTL. It's one of these horrible multiplex system calls that does many things to processes. And one of the things you can do is say, oh, I want to have a Seccomp filter. Now, you can choose which system calls the application is going to be allowed to make or which ones are going to be disallowed. So you're no longer restricted to a fixed set of 4 system calls. You can actually design a filter that say, this program's allowed to make this set of system calls, or it's disallowed from making this set of system calls. People had wanted this facility for quite a long time before this was actually implemented, and there were several proposals to implement this feature, implement system call limitation in the kernel over the years, and they were all rejected by kernel developers as being overly complicated or perhaps too difficult to maintain. And so there was already, by this time, a lot of interest in having a feature like this. And once the feature was added, a whole lot of applications started using it pretty smartly. So the web browsers are using it to do things like sandbox rendering processes. OpenSSH even uses it, I'm not even sure why. There's even some FTP daemons that use it. Systemd uses it. Systemd uses everything. They really do. They love to find what they can use. Things like the container frameworks, they're using Seccomp among many other things. And then there's tools like Flatpak and Firejail, which are pretty interesting tools. If you don't know about them, I suggest it's worth investigating them. Firejail is a sort of generalized sandboxing mechanism that you can use to run some arbitrary application or some standard application with a pre-packaged set of sandboxing rules. Flatpak is a kind of packaging mechanism where you can create packages that can be run on any distribution, in effect. Work's still going on Seccomp. Even in recent times, there's been quite a bit of development. But in 2014, one of the other new features one of the other new details that appeared was there was a new system call added called Seccomp. Now, Seccomp effectively takes the multiplexed piece out of PRCTL, puts it in its own system call, and at the same time, the motivation for adding the system call was we're going to add some new functionality as well. So nowadays, you can set up Seccomp filters using either PRCTL or you can use Seccomp and get a few more features while you do it. Okay, so when we're doing Seccomp filtering, what you're doing is filtering of system calls based on the system call number and the system call arguments. Now, there's one point that I want to bring out here. You can check on the system call number, you can check on the arguments. What you're looking at here is the register values. If those registers contain pointers, you can't dereference the pointers. Obviously, that might be an interesting thing that you might want to do. It's currently not possible. You can just look at the values of the arguments themselves, the values in the registers. There is someone who's working on trying to extend this feature, because if you have a pointer argument that perhaps points to a path name, it might be quite interesting to dereference that path name and see what the path name is as part of your filtering. Can't do that yet. There is someone working on it. They've been working on it for about 2 years. It's quite a big piece of work to get into the kernel, so it is taking a while. And of course, we can't be sure it'll get there, but the work keeps going. I think it'll get there one day. Now, how do we do this? The first thing we do is we construct a filter program, which is basically just some binary instructions inside our C program or whatever else. This filter program is expressed in a certain kind of syntax called Berkeley packet filter syntax. I'll come back to that and look at it in more detail in a moment. Then you install the filter into the kernel using either the Seccomp or the PRCTL system call, and then you execute some code that you don't necessarily trust. Okay, you exec a new program, or perhaps you've dynamically loaded a shared library, in other words, some sort of plugin functionality, and you are going to now execute some code out of that plugin. Once you've done that, now every system call that the process makes is going to be tested against that filter to see, is this system call allowed or not? Once you've installed that filter, you can't remove it. When you think about what we're doing here, we're about to execute untrusted code. We don't want the untrusted code to actually remove the controls that are being placed on it. So installing Seccomp filters is permanent. Now, these Seccomp filters, they're expressed in Berkeley packet filter syntax, they're Berkeley packet filter programs. It's quite likely that even if you've never heard of Seccomp or never done anything much with Seccomp, that you've heard of BPF, because BPF has been around for a long, long time. On Linux, it's been, well, so I'll rephrase that. No, it's been around just generally since 1992. And the reason it appeared is because it was used by TCP dump. Now, what TCP dump does for you is let you look at packets from the network. The notable feature about network traffic, of course, is there's a lot of it. And usually, you only want to look at some small piece of it, the conversation going on between two endpoints. So what TCP dump needs to do is some filtering. So it shows you just the packets that are relevant for you. And so there's a lot of packets to be filtered. Now, I don't know how TCP dump did it back in the mists of time in the very beginning, but one theoretical implementation for TCP dump would be the program puts the network interface into promiscuous mode, just grabs all the packets off the network, and then looks at those packets that have got into user space and decide which packets are interesting according to what the user specified. The problem with doing that is simply the act of pumping all those packets across the kernel user space boundary puts a very high load on the system. Just that transfer of data is very expensive. So what BPF does is what BPF allowed TCP dump to do was to put a filter inside the kernel, and that filter made some decisions about which packets were interesting by looking at the network headers. And then if the filter said, yes, that packet is interesting, then the kernel transferred it across the kernel user space boundary. So now there was only a small amount of information coming across the kernel user space boundary, much less load on the system. Okay, so BPF, what it's doing in effect is to define a virtual machine, and that virtual machine's implemented inside the kernel. The virtual machine has a few notable characteristics. It's got a very simple instruction set. There's only a small set of instructions. They're all the same size. This means that for the kernel to implement that virtual machine, it can be done simply, and the implementation can be fast. There are jump instructions, branch instructions inside BPF programs, but the only thing you can do is jump forward in the code, so you know that the program is going to terminate. You know, these BPF programs being constructed from user space, and they're being put into the kernel, we certainly wouldn't want to have BPF being able to be used as a mechanism to attack the kernel itself. If we could put a program inside the kernel that had a loop and created some sort of denial of service attack against the kernel itself. You can't do that with BPF because you can only branch forward. What this means is the kernel can do a lot of checks to make sure that programs are valid and safe. The kernel knows every program is going to complete it because it's a directed acyclic graph. It only goes forward. The instruction set is simple, so the kernel can easily and quickly verify the operation codes and their arguments. The kernel can even do things like detecting dead code, where there's some block of code in the BPF program where there's a jump over that code, but no jump into the code. If you try and load a program like that, a BPF program like that, into the kernel rejects it and says this is invalid. One of the other things that the kernel can do is verify that every pathway out of the code completes with a return instruction. And a return instruction is the way the BPF program tells the kernel, do I like what I saw or not? Okay, and then the kernel can use that information to make a decision about what to do. Now, back in the days of TCP dump, the return instruction was in effect telling the kernel, do we pass the network packet across the kernel user space boundary or not? But with Seccomp, what it's doing is saying, are we going to allow this system call to proceed or not? There's a limitation on the size of BPF programs, 4K of instructions. It seems to be enough to keep most people happy. In fact, what we'll come to later on is you can install multiple BPF filters, and you can have up to 32K of instructions in total across all the BPF filters. Okay, so we've got this notion then of the virtual machine. It's got some instructions. This virtual machine has a few characteristics. It's got an accumulator register where you do operations with various virtual machine instructions. It's a 32-bit accumulator. There's a data area. The data area is information that can be used by the BPF program. Back in TCP dump days, or when we were using TCP dump, the data area is actually the network packet header. When it comes to system calls, the data area is information about the system call. That is to say, things like the system call number and the system call arguments. There's instructions for this virtual machine. They're all, as I mentioned, 64 bits long. There's a fixed format expressed in C. And this is a definition out of the header files. The instructions all look like this. And you can see here the structure that's used to express this is called sock filter. This tells us about the networking origins of BPF, socket filter. There's a 16-bit opcode. Down at the end there's a 32-bit operand. And then there's two offsets that are used in jump instructions. You can have a jump true on a conditional and a jump false on a conditional, and you can have an offset of up to 255 bytes when you do these jumps. It's a virtual machine that gives you the sort of things you'd expect out of a simple assembler. You've got load instructions. There's store instructions where you can store information into some working memory space that's available to you. One thing, I don't know if I had it on a slide already, one thing about BPF programs is you can use them to inspect system calls and their arguments. You can't change the system calls and their arguments. There's a jump instruction for jumping to another, an unconditional jump instruction. There's conditional and unconditional jump instructions. There's the usual sort of arithmetic and logic instructions, you know, shift, add, XOR, and so on, the sort of things you'd expect. And then there's these return instructions. The return instruction terminates processing of the filter and gives some information back to the kernel saying, what do we think about this system call? Is it good or is it bad? So we've got conditional and unconditional jump instructions. The conditional jump instructions, they consist of an opcode. The opcode says what kind of test do we want to do, equal, less than, not equal, and so on. A value that we want to test against, and then, as I mentioned already, two jump targets. You know, if the condition tests true, jump by this number of instructions. If the condition tests false, jump by a different number of instructions. And we've got instructions, the sort of expected stuff like jump equal. Is the value in the accumulator equal to a certain value? Jump greater than or equal. Jump set. Do a bit test. Are some bits in the accumulator set? What we don't have, and it seems a little surprising at first until you have a little insight, is there's no jump not equal or jump less than or jump less than or equal, because these are all equivalent to the false branches of some other instruction. So the false branch from jump equal is jump not equal. Okay. Now, The targets for these jumps, they're expressed as relative offsets in the instruction list. 0, of course, means no jump. In other words, do the very next instruction. Otherwise, you can jump up to 255 instructions forward. If you want to jump further than that, there's a jump always instruction, an unconditional jump, where the offset that you're jumping is in the operand, the K field of that structure I showed you earlier on. So, yeah, that's way more bits than you need to express how far you want to jump, because a BPF program can only be 4 kilobytes. 4 kilo instructions. Okay, now this is a point I mentioned already. Seccomp provides, or the Seccomp facility provides the BPF program with information about the system call in a buffer that is read-only, so we can't change the system call or its arguments. And that structure can be expressed as a C structure. And there is a structure definition like this in the header files. Struct seccomp data, and we get various information about the system call. First of all, we get the system call number, and then the next thing we get is the system call architecture, and there'll be a number in here that tells us what architecture is this program executing on. And you'll see, and there are constants in one of the header files that correspond to the various numbers here, for instance x86-64 or ARM or whatever. We'll see why this is relevant in a little while. Then another piece of information we get inside this structure is the instruction pointer. Now this is the instruction pointer in the real program that is being filtered. So it's telling us from where is this system call being made. And then we get the arguments of the system call themselves. And we have 64-bit arguments, okay, because arguments can be up to 64 bits on some architectures, and there are up to 6 arguments, because on Linux the maximum number of arguments that a system call can have is 6. Now obviously a lot of system calls don't use as many as 6 arguments. So when you're writing your filter, if you're going to look at a certain system call and its arguments, of course you need to know how many arguments does that system call deal with, and you'll only use certain pieces then out of that arguments part of the data. So you could code your BPF programs completely in binary if you want, but as a first cut, there are some macros and symbolic constants in the header files to make your life just a little bit easier. And in particular, there's a macro called BPF Statement. You give it an opcode and an operand, and what it's doing is just constructing the initializer for that 64-bit structure, which has 4 fields. There's the opcode, 0 for the 2 jump offsets, and then the operand at the end. And then same thing for the jump instruction, but this time a couple more arguments to the macro, the offsets for the jump true and the jump false target. Again, we're constructing this initializer for the 64-bit structure. So then just to look at a first complete instruction example, then here we've got a BPF statement. We're building some sort of statement. The statement we're building, the first part here is the operand, and the operand is being constructed by ORing together various bits that construct the operand. And BPF load here says this is a load instruction. The W there says the size of the object we're loading is a word, 4 bytes. And the abs part there says this word is coming from the data area, because you could do loads from, say, the so-called working memory of the Seccomp program. So load a word from the data area, and then the question is, which word from the data area? Let's go back a second. Here was that data area. It's got various pieces. It's expressed as a structure. Now, I don't know. I often find that when I talk about this, people haven't come across this handy little macro here called offset of. Who's seen it? Who's seen offset of before, just out of curiosity? Yeah. What offset off does is you give it two arguments. One is the name of a structure, and the other is a field in that structure. And what it does is return you the byte offset of that field in the structure. So we're saying, give me the byte offset of the arch field in the Seccomp data structure. What's offset of going to return in that case? 4. Yeah, because there's an int beforehand, 4-byte int, and then arch is the next thing. Okay. Alrighty, let's try another instruction. BPF Jump. This is a jump instruction. The kind of jump we're doing, it's a jump testing on a quality. Is the value in the accumulator equal to a certain value? What value? Well, the value is taken from the operand. That's what the BPFK part is saying. So is the value in the accumulator equal to the value in the operand? And what's the value in the operand? It's this thing, the constant for the architecture x86-64. And then if that test is true, we're going to jump forward 1 instruction. In other words, skip the next instruction. Otherwise, we're going to jump forward 0 instructions. Do the very next instruction. Okay. I think I've covered all of that. Alrighty. Now here's another example of an instruction. This is a return instruction. Terminating the execution of the BPF filter, telling the kernel what have we decided about this system call. And here we're saying BPF return, and we're going to return a value that is in the operand. So when we return, we give some information to the kernel. And the value we're giving in the operand is this value here, seccomp ret kill process. And this is our way of saying, we don't like this system call. We don't like it so much, you should kill the process. Okay, some other examples here. Here's an example of an add operation, arithmetic and logic instruction. It's an add where we're saying add the value in the operand to the accumulator, and the value in the operand is 1. So increment the accumulator. Or we can do things as well, like for instance doing right shift of a value in the accumulator, arithmetic logic instruction, right shift by the number of bits specified in the operand. Shift right 12 bits. Now, I talked about this architecture field that's in the Seccomp data structure, and the reason that field exists there is because checking the architecture value needs to be the very first step in the execution of any BPF program. And one of the reasons for that is that system call numbers are different on different architectures. You know, the system call numbers on ARM are different from the system call numbers on x86, which are different from the system call numbers on PowerPC, and so on. And you might have created a BPF program on one architecture and you actually stored it in a file. So you've got a blob somewhere which is a Seccomp program, and then later on you load that blob into some application because you're going to install it as a Seccomp filter for that application. But you happened to create the filter on, let's say, x86, but accidentally, because of a configuration mismanagement in your setup, you loaded the program on, let's say, PowerPC, the BPF program, and you tried to install it. Well, now that BPF program is going to be making systems using x86 system call numbers, which are different from PowerPC system call numbers. So in other words, the program's going to make the wrong decisions, unless at the very start of your program you have a piece of code that, in the BPF program, that says, is this architecture the one I expected? Am I actually executing on the architecture I expected? There's even some more subtleties than this. I talked about the difference between, say, x86 and ARM and PowerPC, but you've got many cases of modern hardware now that supports multiple system call conventions. Modern x86 hardware supports 3 different system call ABI conventions. There's x86-64, the modern x86, there's i386, the ancient 32-bit instruction set, which has different system call numbers. And there's another one nowadays called x32, which is 32-bit pointers and longs on x86-64 architecture, which again has different system call numbers because the arguments are different sizes. Even though it's also running on x86-64, there needs to be different system call numbers in some cases because some system calls take longs and pointers and as arguments, and they're different sizes on x32. So even if you're writing your BPF program to run on just one architecture and you load on that architecture or on that hardware platform, actually the system call ABI that's being used by a particular program might be one of several things. And even over the life of a process, this might change. You might have a process executing an x86-64 64-bit program, but then it execs a 32-bit binary. It's still the same process, okay? But now it's using different system call numbers. But during the life of a process, the system call ABI might change, but the scope of BPF filters is the lifetime of the process. Okay, so the filter must check its assumptions about the architecture. Okay, so system call, these BPF filters return a value. A filter gets installed, every system call gets tested against that value, and the system call filter returns a value telling us whether the system call's allowed or not. That return value is split into, it's 32 bits split into two parts. 16 bits say what is the action we want to take in response to that system call, and then there might be some data that goes along with that action. And possible actions that we have: seccomp ret allow. This system call's fine, let it proceed. Seccomp ret kill process. We really don't like this system call. Kill the process and do a core dump. Now it looks, I'll rephrase this. The process is killed. It looks like the process was killed with a SIG-sys signal. There is no signal involved. The process is dead. But any other process that was monitoring this process, say using ptrace or wait PID, it will appear that that process was killed by a SIG-sys signal. Another possibility is kill the thread that made the system call. Or, okay, we don't like the system call, but don't kill the thread or the process. Make it return an error. Don't actually execute the system call, cause it to return a failure status with a certain error, and the error is whatever value we specified in the bottom 16 bits of the return value. There's a few other possibilities as well, which I won't try and walk through. Okay, so using these BPF programs, let's drill down a little bit further. The general idea is then a process builds a filter and then it installs it using one of these system calls. With the system calls, what you do, let's focus on seccomp. You say, I want to install a filter. So this is a flag spit mask, which I won't go into. And then there's a pointer to the filter program. And the filter program looks like this. It's a struct socket filter program, again, networking origins, where you've got the size of the program, the size of the BPF program, the number of instructions, and then a pointer to the instructions themselves. Now, if you want to install a filter, one of two things must be true. Either the program must be privileged, or you've set a flag called no new privs for the process. The way you do that is with this system call. Now, let's step back a second. Why is that necessary? Suppose you're an attacker who wants to compromise a privileged program, and you know about Seccomp, and the idea you have in your mind is, people who write setuid programs, setuid root programs, they're not always as careful as they should be. And maybe there's an error, a code path in the setuid root program where the programmer didn't carefully check the return value or gracefully handle a failure from a certain system call because the programmer expected that system call would always succeed, for example. And then you say, okay, as the attacker, I'm going to set up a filter. And then I'm going to run that setuid program. I'm going to exec that setuid program. And then the program's going to misbehave and do something unexpected while it's privileged. Attackers love that sort of thing, of course. You can't do that. Because if you're an unprivileged user, the attacker, you have to set this bit, and the effect of this bit on a process is to disable the effect of setuid programs and setJIT programs and programs that have capabilities. So this means an attacker can't do the kind of exploit I was talking about. So let's look at a small, complete example now. What I've got here, my main program, I'm setting this no new privs bit. That's the first thing I must do before I install a filter. Then I've got a call to a function which installs the filter. We'll look at that in a moment. And then my program calls the open system call, and then line 8 there's a message tellingly we shouldn't see this line or shouldn't see this message. Okay, and that's because the filter is going to cause the open system call, or it's going to, when the open system call is made, the filter is going to tell the kernel to kill the program. Okay, what have we got? Here's our install filter function, and the very first thing here is I've got a struct sock filter array, which is the instructions of my BPF filter. First thing I'm doing, load a word from the data area. The word I'm loading is the offset of the architecture. In other words, load the architecture into the accumulator. Then do a jump equality test. Is the word in the accumulator equal to the value in the operand? The value in the operand is this constant arch x86-64. I'm asking, am I currently executing on x86-64? If I am, I'm going to jump forward 1 instruction, skip the next instruction. Otherwise, I'm going to jump forward 0 instructions, kill the process. Okay, we're not on the architecture we expected. This means the system call numbers are different from what we are designed for. Stop. Okay, but otherwise, the next thing that happens is we load a word from the data area. The word we're loading this time is the offset of the system call number. So load the system call number into the accumulator. And then we have an equality test. Is the word in the accumulator equal to the value in the operand? Is it the open system call number? Okay, this thing here, nr open, is just a standard constant in the header files. There's these constants for every system call number for this architecture. Is the system call number equal to open? If it is, we're going to jump forward 2 instructions. 0, 1, 2, kill the process. Otherwise, we're going to jump forward 0 instructions. Do an equality test. Is the word in the accumulator equal to the open at system call number? Now, open at is a more modern version of open. So I want to make sure that neither of those things is allowed. In fact, the open wrapper function in glibc nowadays calls open at the system call, not open the system call. And if it is equal to open at, jump forward 1 instruction, kill the process. Otherwise, jump forward 0 instructions. And here I say, return to the kernel, allow this system call. So every other system call is allowed. Alrighty, now there's the definition of my struct sock fprog. It's the size of my filter program, which is the size of the filter divided by the size of the first instruction. So, because it's supposed to be the number of instructions, not the number of bytes. And then I set the filter field to point to the filter program that I've just constructed just above. And then I install the filter using Seccomp set mode filter pointed to my filter program. And then when I run that program, what I see is there was no output from the printf because the open system call, the open at system call to be more precise, caused the kernel to kill this process. And it was killed as though it had been killed with a sig-sys signal. And when the shell sees that the process that it started looked like it was killed with a SIG-sys signal, it prints out the standard textual description of the SIG-sys signal, which is, in the English locale, bad system call. Dollar question mark here, the status of the last command. For a signal, the status of the last command is 128 plus the signal number, and signal number 31 is SIG-sys on this architecture. Okay, I'm going to skip another example because we are running a little short on time. Okay, now, if you've got some existing filters that allow you to use PRCTL or Seccomp, you can add further filters that further restrict what the program can do. You can have an arbitrary number of filters, but the total number of instructions in all the filters is 32K. And when a system call is executed, when a system call is made, all of the filters are executed in reverse order of registration. Each one of those filters gives you back a return value. The kernel executes all the filters, and then it says, I'm going to do the action of the first filter of the highest priority. And there's a priority of filters. Seccomp kill process, ret kill process is highest priority. Seccomp ret allow is lowest priority. The reason that for this first scene action is that you might have several filters that return Seccomp ret erno, and that's the high, and perhaps that's the highest priority that is returned by any of the filters. The first filter that returned an erno value, that will be the erno value that is used. If you have Seccomp filters that allow you to do fork or clone, the child inherits the parent's Seccomp filters. If the filters allow you to do execv to load a new program, the filters are preserved across the execv, which is another way of saying you can't escape filtering by creating child processes or executing a new program. Okay, these filters are executed for every system call. There is a performance cost on the filter I showed you already, which was denying the open system call. That means 6 BPF instructions per system call. If I instead apply that filter to a program where I call get PPID, get parent process ID, repeatedly, then, which is one of the cheapest system calls, just by the way, I find that the execution time of the program goes up 25%. Of course, these days with Spectre and Meltdown, that statistic I realize is no longer valid because Spectre and Meltdown mitigations increase the execution time of get PPID by a factor of 4. Ouch. Okay, let's forget about Spectre and Meltdown and so on for a moment. But 25% on what it used to be. Okay, now that seems reasonably high, but remember get PPID is a cheap system call, and programs don't spend all their time making system calls. If you're writing a filter that deals with many different system calls, then obviously the order in which you do the checks in your filter can matter. And you want to construct your filter so that the commonly applicable rules are dealt with first, so you can exit the filter as early as possible. In the ideal world, where you get the perfect binary chop on your checks, you'll get order log n performance on your filter, where n is the number of different kinds of checks that you're going to make. Obviously not probably possible to achieve in practice, but it's the ideal to aim for. Okay. So I said that when Seccomp appeared, people started using this because they'd wanted this for a long time. But I just want to give you a few warnings about using Seccomp, because it is a sharp knife. One of the things that you're going to try and answer when you want to put a Seccomp filter onto an application is, which system calls does my application make? And it's actually not always very easy to discover that sort of information. You could try doing a source code audit, but hey, what about all the libraries that your application uses? You could try doing an strace on your code, but that'll only tell you about the code paths that were taken. Perhaps you can do straces with many different inputs where you try and execute all the code paths, but there'll probably be one or two that you miss. Okay, now, What about that? You might write a Seccomp filter that allows a certain set of system calls, disallows all the other ones you think are illegitimate, but you missed one. And it's a system call that is hardly ever made, but one day your program makes that system call because of some obscure code path. And at that point, your application gets killed because it made a legitimate action. Congratulations, you've just used Seccomp to introduce a bug into your application. Those kinds of bugs can be pretty hard to find during testing because we're talking about obscure code paths. Another thing to think about is system call filtering is based on system call numbers, but applications use C library wrapper functions, at least normally. But the wrapper library function behavior might change across glibc versions. For instance, until glibc 2.26, the open wrapper function on some architectures underneath used the open system call, but on x86 and on x86 used the open system call. But in 2.26, it changed to using the open at system call. So if you're trying to filter for just open, your filter wasn't catching open at. There's a relevant article there on LWN, the inherent fragility of Seccomp. What I'm trying to say here is, you can't just create your Seccomp filters and forget about them. They need to be tested like every other piece of code in your application, and they need to be part of your continuous integration testing because things change over time, and you need to have unit tests for your Seccomp filters as well. Okay, now just very quickly, there are obviously those pseudo assembler instructions I was showing you before, that's painful. There are some higher level tools. Perhaps the one that you most likely to reach for is something called Lubeset Comp. And Lubeset Comp, basically it's a library where you can say, I want to make you make a bunch of API calls saying I want rules to do this, this, and this. And then at the end you get you have an API button where you can squirt out the blob, which is the BPF program. It's actually really nice. It's got a full set of manual pages with examples. It's almost like the person who did this wanted people to use it. Okay, so just a little flavor of how Lubeset Comp works. The fundamental data structure is something called a Seccomp Context, and it's just used to hang the rules off in preparation for pressing the API button that says, give me the BPF code. So you initialize this thing, and then we say add a rule here. In this case, I'm saying add a rule that if there's a system call clone made, fail with the error eperm. Add another rule that says if we make a fork system call, then fail with the e-not sup error. Then we say load that filter into the kernel. And that does all the steps of things like disabling or setting no new privs and the seccomp call that it installs the filter. And then my program tries to call fork, and at that point it promptly gets killed. Okay, there's the example. There is some other tools. There is a BPF compiler, so to speak. It lets you write a sort of pseudo-assembler with symbolic labels, so you don't need to count offsets anymore, and you can compile that to BPF. It's part of the NetSniff NG project. There is, and this is sort of off on a little bit of a tangent nowadays, there is, I said before, when I put my filter onto the program that called get PPID repeatedly, it was plus 25%. I didn't say at the time there, it was plus 25% without the JIT compiler enabled. There is a JIT compiler in the kernel for BPF, which converts the BPF program into native code on that architecture, and therefore it executes quicker. They say 2 to 3 times better. I've seen even better than that in some of my test cases at least. The JIT compiler on most architectures used to be disabled by default. You can now enable it, and then you could enable it by writing 1 to a certain file. A lot of modern, recent distributions have actually set a kernel option that is available since a few releases to actually have the JIT compiler always on. Okay, oh look, broadly, applications. There's 2 broad applications I think for Seccomp. One is you're doing sandboxing. In other words, you want to prevent an application from making any but a restricted set of system calls. So you use a whitelist approach where you block all system calls by default, but you allow a few system calls. This is what most of the applications I mentioned earlier are doing, things like the container frameworks and Flatpak and the browsers. But there's an alternative which is interesting, which is failure mode testing. You've got an application which makes certain system calls, and those system calls hardly ever fail. And so how do you test whether your application gracefully handles failures in those system calls? Well, one way of doing this is to use Seccomp, where you install a Seccomp filter that causes that system call to fail. Okay. Now, this then is just some further information you can find out about Seccomp in various places. This last piece here actually is a write-up of this presentation that was done by someone at lwn.net, or a version of it I did 2 or 3 years ago. Okay. Thank you very much for your time. The slides are available here. The source code is available here. I do training courses. Lots of training courses. I wrote a book. Thank you for your time. And I'll take questions if there are, but we were really short of time, so I don't know, well, we're short of time. If there's any quick questions, I can take them, or you can grab me as I leave. Yes? Yeah, so you install the filter you install the process installs a filter for itself, and then the lifetime of that filter is until the process terminates. Yes.
So you said that the maximum size was 32K for this.
The total size of you can have multiple filters. And the total number of instructions across all the filters is 32K. Each individual filter can be 4K instructions.
So what happens if the attacker tries to just fill up all of those 32K and then your application?
Yeah, but hang on. The attacker is running inside that application. Yes, it's.
I see your point.
Yeah. Yeah. So you're saying, what if the attacker makes their own life even more difficult?
But what would happen if you can't install the filter? Will the program just die?
No, you'll get an error when you try and install the next filter that exceeds the limit.
Okay.
Yeah.
So you have to have error checking on the filter installation.
Yes, if you don't check the error, you won't know that you failed to install the filter.
Okay. Thank you.
Okay. Thank you.